Losses in strip line. In this session, you will be learning about the losses in strip line. And in the earlier classes, you have come to know about the various types of strip line, that is microstrip line, parallel strip line, coplanar strip line, and shaded strip line. But the major losses occur in microstrip lines and parallel strip line. There are four different losses. The four different losses are dielectric loss, it is dielectric loss, ohmic loss, radiation loss, and attenuation loss. The dielectric loss occurs, the dielectric loss, ohmic loss, and radiation loss we can find in microstrip line, whereas attenuation loss is found in parallel strip lines. So, what are these losses and what is the reason for this loss? So, as we all know, a microstrip line consists of the ground plane upon which there is a dielectric substrate, and on the dielectric substrate there is a strip conductor. So, and here one more thing is the dielectric substrate which we make use is a non-magnetic dielectric substrate. Always you choose that such that the dielectric substrate is non-magnetic. So there are two types of losses which occurs predominantly in microstrip lines. They are dielectric loss and ohmic loss and radiation loss. The dielectric loss is the loss which occurs in the substrate material, because due to the variations of the dielectric substrate, the dielectric losses will occur, and the ohmic loss in the strip line is due to the strip conductor and the ground plane. Means what is the conductance, what is the leakage capacitance or is leakage signal from the strip to the ground, conduction to the ground, there occurs the ohmic loss. And always whenever we want to express the losses in for microstrip line, we sum up this dielectric loss and the ohmic loss, and they are expressed in terms of loss per unit length and in terms of factor known as attenuation factor alpha, because a loss is the one where the degradation of the signal will take place, because whenever a loss occurs, then suppose if you are transmitting a signal of 2 gigahertz through the dielectric through the device, then instead of 2 gigahertz, the final output what you get it will be around 1.8 gigahertz. So 0.2 gigahertz is the loss in the transmitted signal, and this loss would be due to the fluctuations in the dielectric substrate, or else it would be some corrosion on the strip line, that is the conductor, and it would also be conducting of the electrons from your conductor to the ground plane. Whenever more number of electrons get transmitted, the diverts towards the ground plane, then also percentage of loss is more. So that's why what we do is whenever we are expressing the loss in any type of the strip lines, we express them in the order of loss per unit length, because in a strip line the width and thickness of the strips are important, and also the thickness of the height of the dielectric substrate is also important. So that's why the loss is expressed in terms of loss per unit length, and they are also expressed as attenuation factor, which is alpha. So the dielectric loss in a microstrip line is due to the percentage of loss that has occurred due to the effect in dielectric substrate, and ohmic loss is a loss which is resulted due to the conducting strip and a strip line, where the signal may propagate from strip to the ground plane. And thirdly, the radiation loss. The radiation loss is due to the uh, um, conductor itself once again, where the percentage of radiation the conductor can allow the signal to propagate further is what we call it as radiation loss. So first of all, coming for the dielectric loss. In a lossy dielectric material, always the conductivity cannot be neglected, because suppose if we neglect, always the conductivity results in the electric and magnetic fields in the dielectric, and they are no longer in terms of time. So whenever this is the condition, then the dielectric attenuation constant is expressed by the equation alpha d is equal to sigma by 2 into root of mu by epsilon nepers per centimeter. Okay, so dielectric loss can be found out by the equation, that is alpha d is equal to sigma by 2 into root of mu by epsilon. So if you want to calculate dielectric loss due to dielectric material, this is the equation what you are supposed to find. Once again, the dielectric constant can always be expressed in terms of dielectric loss tangent, where it is tan theta is equal to sigma by omega into epsilon. So, whenever I substitute this above equation with the dielectric attenuation constant, then I can express the attenuation constant as alpha d is equal to omega by 2 into root of mu epsilon into tan theta nipple per centimeter. Okay, so you can understand that we are expressing the unit in terms of per meter length. Okay, and as we are making use of microstrip line, the microstrip line is a non-magnetic mixed dielectric system, where the upper dielectric above the microstrip ribbon is air. Okay, so due to that reason, the dielectric loss will vary. And one contribution by the scientists by name Welch and Part, they derived an expression for the attenuation constant of the dielectric substrate, that is alpha d is equal to 1.634 into 10 to the power 3 q sigma divided by epsilon rd decibel per centimeter. So you can see here, until this point it was expressed in nepers per centimeter, but here we are expressing the loss as dB per centimeter. So alpha d is attenuation constant, where it is dielectric attenuation constant, and it is expressed in terms of 1.634 into 10 to the power 3 into q sigma divided by epsilon rd decibel per centimeter. And whenever the dielectric filling factor, where the dielectric filling factor S, which is Q is equal to epsilon Re minus 1 divided by epsilon R minus 1. So we can express attenuation constant per wavelength as alpha D is equal to 27.3 into Q epsilon R by epsilon Re into tan theta by epsilon lambda G dB per lambda G. Is decibel loss in accordance to the wavelength of the waveguide, or is wavelength of the conducting strip. And here in all this, the main important thing is the equations which you have obtained is not by means of derivation. You don't have any derivations. In the exam also, you need to explain what is dielectric loss and write the equations which has been given. No derivation is there for this topic. Okay, and all these are already derived equations which are called as empirical equations, and no one can change. That's why you need to just remember the equations and write down in the exam. There is no derivation which is given in the textbook, or is as they are empirical equations, it is self-explanatory. So this is about the dielectric laws. The dielectric laws is the resultant of the lossy dielectric material which is present in the strip line, and whenever the conductivity is taking care, the results like electric and magnetic fields and dielectrics which are in phase of the time should not be neglected. So that's why you express the dielectric constant in terms of attenuation constant, that is alpha d is equal to sigma by 2 into root of mu by epsilon fs per centimeter. And that dielectric constant can also be expressed in terms of dielectric loss tangent, that is tan theta is equal to sigma by omega epsilon. So finally, we can express the attention constant per wavelength as alpha d is equal to 27.3 into q epsilon r by epsilon re, that is relative dielectric constant and effective dielectric constant. Okay. So epsilon re is relative dielectric constant and epsilon r is effective relative constant, tan theta by lambda g. Okay. So this is about the dielectric laws. And next is ohmic laws. The ohmic laws is second type of laws which we can find in microstrip line. And as we all know, in a microstrip line, it has a low loss dielectric substrate where the predominant sources of loss at the microfrequency are not or non-perfect semiconductor, non-perfect conductors. So as we all know, the strip lines are consist of the material which are semiconductors. Means the dielectric substrate what we are using is a semiconductor. That is, it would be N-place substrate material or is P-place substrate material. So as they are not perfect conductors, the ohmic losses will result in a microstrip line. And always the current density in the strip conductor and the ground conductor is not uniform. So the microstrip conductor contributes for the major part of ohmic loss. Okay. So the conductor, whichever is there on the conducting path, that is the microstrip, is the one which leads to maximum ohmic loss, majority of the ohmic loss in the semiconductor. So the equations for ohmic loss in terms of attenuation constant is given by the equation, that is for a wide microstrip line is given by the equation alpha c is equal to 8.686 Rs divided by Z0 into omega dB per centimeter, under the condition that W by H is very much is greater than 1. Okay. The ohmic loss can be found in a parallel strip line and a microstrip line as well. And the conducting attenuation constant due to ohmic loss in a microstrip line is calculated by the equation alpha c is equal to 8.686 Rs divided by Z0 into omega, and it is in terms of dB per centimeter. And this condition to find out the attenuation constant will hold good only when W by H is greater than 1. And coming for the equations of Rs is root of pi f mu divided by sigma, and series resistance or a surface skin resistance, it is 1 by delta sigma, and where delta is equal to root of 1 by pi f into mu sigma, where it is a skin depth in centimeter. Delta stands for skin depth. So this is about the ohmic loss, where the ohmic loss is resulted in the microstrip line due to the strip conductor. And the third one is radiation loss. The radiation loss is once again found in a microstrip line, where the radiation loss always depends upon the substrate's thickness and dielectric constant. And the person who has written the who has arrived at the equations for radiation to find radiation losses 11. The results which were demonstrated by the Levin shows that the ratio of radiated power to total dissipated power for an open circuit microstrip line is P radiated power divided by the transmitted power. P RAD stands for power radiated and PT is power transmitted. So the ratio of radiated power to the total dissipated power is equal to 240 pi square into h by lambda naught square into F epsilon RE by Z naught, where F epsilon RE is a radiation factor. And always the radiation factor is found out by the equation FRE is equal to, this is the equation for finding out the radiation pattern. It is FRE is equal to epsilon RE plus 1 divided by epsilon RE minus epsilon RE minus 1 divided by twice of epsilon RE into root of epsilon RE ln root of epsilon RE plus 1 divided by root of epsilon RE minus 1. So, the radiation loss is the resultant of the thickness of the substrate and the thickness of the dielectric constant. So, if you want to find out what is the radiation loss by means of ratio, then you should know what is the radiation factor, where the radiation factor is obtained by the equation F into epsilon RE. And coming for the radiation pattern, always the radiation factor decreases with increasing substrate dielectric constant. So alternatively, the above expression can be expressed as power radiated by power transmitted is equal to R by Z naught, where RR is radiation resistance of an open circuited microstrip line. And we also have an equation for radiation resistance. It is RR is equal to 40 pi square into h by lambda naught whole square F into epsilon RE. Okay. So, the ratio of radiation resistance to the real part of the characteristic impedance Z naught of a microstrip line is always equal to the small fraction of power radiated from a single open circuit discontinuity. And always we should keep in mind that the radiation loss decreases when the characteristic impedance decreases, that is Z naught. When Z naught decreases, the radiation loss decreases. Okay, it's vice versa. Whenever the Z naught increases, the radiation loss decreases. So, always for a low dielectric constant substrate, the radiation is a significant high impedance level, is at high impedance levels. So, this is about radiation loss. Our next is attenuation loss. The attenuation loss is a loss which we can find in majority of the parallel strip lines. So, in attenuation loss, always the attenuation is more, or else the attenuation loss is calculated for the strip lines where they are conducted in parallel. And the propagation constant of a parallel strip line at microwave frequency can be expressed by the equation gamma is equal to root of R plus j omega L into G plus j omega C. for the condition R is less than omega L and G is less than omega C. So under this condition, we can derive the attenuation loss as gamma is equal to half into R into root of C by L plus G into L by C plus J omega into root of LC. Okay. So the attenuation phase constant for a parallel strip line is given by the equation alpha is equal to 1 by 2 into R into root C by L plus G into root L by C Nepers per meter. So the unit what you express is also important when you are writing the attenuation loss. And the beta is given by the equation beta is equal to omega by root LC radians per meter. So by substituting the distributed parameters of parallel strip line into the equation, the final equations for the final attenuation constant for conductor and dielectric loss. Yes, that is for conductor loss, it is alpha C, and for dielectric loss, it is alpha D. So alpha C is equal to 1 by D into root of pi F epsilon D divided by sigma C Nepers per meter. And dielectric loss is 188 sigma D divided by root of epsilon RD Nepers per meter. Okay, so these are the two things which can be written for attenuation loss. So attenuation loss for a parallel strip line can be expressed in two forms, that is one is conductor and the dielectric. That is for conductor loss it is alpha C and for dielectric loss it is alpha D. So these are the four types of losses in parallel strip line. So you have learnt about the four types of losses, the four different losses which we come across in strip lines. That is the ohmic loss, the dielectric loss, radiation loss, and the attenuation loss. And in major, we find the dielectric loss, ohmic loss, and radiation loss occurs in microstrip line, whereas the attenuation loss is found in parallel strip line. And relevance to this in the examination, it will be a question. The question will be asked as explain the various losses in strip lines. Depending upon the marks you are supposed to answer. Sometimes it will be 8 marks question where you'll be asked to explain any two losses in strip lines. So when you write the loss, whichever is there, it is also very much essential to write the equations. So please write the equations in relevance to that loss. If we are rewriting the dielectric loss, the equations for alpha D, that is dielectric attenuation constant, is important. And next, the alpha D value, which is final value, you are supposed to write. That is alpha D is equal to 27.3 into Q epsilon R divided by epsilon RE into tan theta by lambda G dB per lambda G. That is wavelength, as per wavelength. And when you are writing the formulas, the final unit, that is in which way you are expressing the value, is also important. So you can expect around 8 marks question in relevance to loss. And in relevance to loss, there is no problem that has been asked in the examination until now. Only it is a theory question what has been asked. Explain the various losses in strip lines.